So let's go. We will start today's session. So basically, today's session I discuss about some advanced topic on agriculture precision. Okay, how we can easily work with that, mainly soil and water management. Okay, so I'll try to explain all of those. Then you can easily get the idea. Okay, let me share my screen.
Shall before?
Yeah, please.
Yes, I got all the material for the last class, but I tried to download the PPT, PowerPoint, so that I can store them in my local drive.
Okay, so I think it's a privately access, so that's why you can get the information from the slide, but you cannot download it in the locally. Yeah, so that's why.
Can you allow?
Okay,
Can you
so let
allow it?
me. Okay,
Because
so I will.
if I want to read it, I must have internet. So sometimes I want to read them while I'm offline.
Okay, no problem. I will try to manage and send you. No problem. Then you can easily get the all of slide in your local computer. No problem. I will send you.
Okay, thank you. Thank you.
Okay, I will send you.
And also, you didn't send me the book. You said that you
Yeah,
will
yeah,
send me some references about
yeah, yeah.
precision agriculture.
Okay, so I'll send you that directly on your email. Then you can easily get from the email. No problem.
Okay, okay, thank you.
So then you can. Okay, so today I discuss about that soil and water management using remote sensing. This topic I try to give the lecture and also show you the all of practical things. Then I hope you can easily get the idea and use this paper technique. Let me open my slide just a minute.
And do you remember about the DSA start method I told you for AD prediction, maybe using the
Okay,
planning I requested?
okay, understand. Okay,
You remember?
yeah.
Oh, okay.
So let's Okay, so basically today should discuss about that agriculture precision and how we can easily management the soil and water. We'll also discuss about that. Okay, and soil and water management in remote sensing. Help of Google Earth Engine. We try to discuss about that. So first of all, today should discuss about this type of topic. Suppose soil moisture, how we can easily monitor the soil moisture, then soil pH. Then we also discuss about that soil health, how we can easily monitor the soil health or soil nutrient. Okay, and then also discuss about that water balance. Okay, so water balance basically it's help you to identify suppose for any specific cropland how much water need. Okay, and it's called the water balance. We also discuss about that, and we also discuss about that crop types analysis by phenological model. So previous class I discussed about that phenological model, but today's we're going to discuss about that how we can easily identify different types of crop. Okay, suppose in a cropland area, different types of crops, suppose rice, sugarcane, or also jute. So this type of crop, how we can easily identify. So basically, every crop we find out that individual or different phenological model for each crop we find out. Okay, we'll also discuss about that. And soil moisture we can also monitor by Landsat or Sentinel-2 satellite imagery. So this session will discuss about that. But soil moisture is also available for that ready-made data, but which is not more better. Okay, basically it's called the MODIS. It's the 9,000 meter. Okay, pixel size. So that's why when you work with small study area, then we face some problem using the MODIS SMAP or soil moisture data. We face some problem. So that's the reason I will discuss about that how we can easily monitor the soil moisture by Landsat or Sentinel-2 satellite imagery. Then you can easily get that. As well as we also discuss about the soil salinity. Okay, soil salinity as well as also soil brightness index. We also discuss about that and how to identify for soil, clay or moisture. This type of thing to explain about that. And also finally, crop water stress index. So it's very important index to identify water stress on the crop. So I'll try to explain all of those step by step, then and also show you the practical example. Then you can easily get the idea all of those, no problem. So let's go. So first of all, soil and water management. Suppose first of all I try to show you the one data set. It's called that SMAP. It is a soil moisture data set, and this data set we can easily combine with Sentinel-2 soil composite. We can also create using the SMAP and Sentinel-2. Okay, so first of all I try to show you this example, then okay, so let's go. I will try to practice it also more better. Okay, so here I add some objective about that. So how we can easily map surface soil moisture absolute using SMAP, or we also identify bad soil composite from the Sentinel-2 and identify to suppress vegetation. Okay, and also compute the soil pixel. We can also compute it the salt, basically salinity, and also compute about that soil brightness. Okay, and visualize and interpret the layer for agronomic decision. We can also get from this type of things. So basically this is our objective. So this objective we try to fill up by this practical. So let's show the practical example. Let me open my code editor. Just yeah. Okay, so first of all, if I just simply search here one data set, soil moisture data set, simply search here soil moisture. So this data set is not much good resolution. So that's the reason we'll discuss about that another data set which is Landsat or Sentinel-2 or Sentinel-1, how we can easily derive the soil moisture information. We'll also discuss about that also, no problem. But you can see this is the one kind of data. It's called the soil moisture. It's daily available data. Okay. So suppose just I open this data. So this one kind of data. It's available from 2015 to 2023 December. And if you check the another data, this is the this one. So it's also available from 2023 to present time. If you check this data time period, so it's available from 2023 to present time. And also check the another data set which is available from 2000 to 2023. So this first one data set. So this data set is available from 2015 to 2023. Okay, both are the same data, but this data set is more update, so we can get that update information about the soil moisture by using this data. So this data set is available from year of 2025 23 August. Okay, so this is the last time period about that this data set. And this data set, if you check this data set, pixel size is a 9000 meter, which is not more good when we are applying for the more small study area or a small cropland. Okay, so but this data set is also a lot of use for the large scale analysis. Suppose for the large or big study area, we can easily identify the soil moisture from here. Okay, so let's go try to use this data set and identify for soil moisture. And further we also, okay, so let's go just simply copy this snippet id. This is the soil moisture snippet id. Just I copy and paste in our code editor. And further just give a variable name. You can put any name. I put the name, suppose take a variable, suppose put the SMAP. You can put any name. Okay, so now this data set we simply filter our study area. Just first of all I simply choose my time period. Suppose I put the filter date. So then you can put your own time period, suppose on your growing season or a specific cropland time period, or growing season start and growing season end. So simply put the time. Suppose I just put the time period year of suppose 2025 01 1st January. Then put here suppose year of 2025 06 suppose 30. Suppose this is my growing season, I simply put in here. So now let's check how many images are available between this time period. Simply use that size function and compute it how many images are available for our study area. Okay, we find out the 179 images are available between this time period. And this dataset have a, you can see this dataset have a different types of band, but now we want to work with the soil moisture. Okay, soil moisture, this band we try to use. Just copy the band name of soil moisture and then just use a select function to select the specific band. Just I select it. Okay, simply select the band. And this data set have a different types of null value. Suppose some place there is no data, so this type of data we can also filter. Okay, so how I can filter the null value? So a lot of time we check, suppose some data set is not available, some place there is no pixel, or there is no value for the specific study area, so then we can also filtering the null data, okay, or null value. So for that, if you check, I have total 179 images. So from these images, I just remove all of null value or all of null pixel. Okay. So for that, just create a function. Okay. Suppose I create a function and I put the element name img and put the curly bracket start and int. In this curly bracket, my argument is that I want to return this image. I want to put the update marks use a condition. Then my condition is this image not equal and null value we replace minus 9999. So it's indicating about the null value. We simply replace, just put the not equal minus 9999. So it means that we remove all of null value from our data set. And now further just clip with our study area. Suppose just like clip without a study area, I put the, suppose I simply import a study area. Okay, let me just simply import, just take a agricultural land, then it will look more better. For example, okay, suppose I take this type of agricultural land, so just draw a this type, this is my boundary. Okay, just I put, and I take the big study area because it's a 9,000 meter square kilometer, 9,000 meter pixel size. Okay, and just I put it's a AOI, and I just click with AOI. So now check. Okay, so now this is the function. This function I need to connect with my collection. So this is my collection. So for that we need to use a function, this function called the map function for connecting. Just use the map function, and this bracket just keep in the last bracket in here. So now run the code. So now it's okay, we find out, you can see 179 images, and all of images we simply remove all of null pixel value from here. So now we just create the composite. Yeah, please. Yeah.
I think that function will not work because we didn't composite the images by media nor min.
Yeah, so now we create the composite. Okay, so now we create the composite using the 179 images. So first of all, we simply choose our image collection, and from this all of images, we simply remove all of null value, all of null pixel value, simply remove using this function. So now this just use this 179 images and this create the composite. Okay, so let's try to create that. Take a variable. Suppose I put the smap, I create the median composite to take the all of middle pixel value of soil moisture. Just call the smap and apply the median. Okay, and now I want to add the layer. So just map dot add layer of this.
Well, we can clip before. After median, you can.
Yeah, so now in this case, this is another way. Suppose in this case, you can see this is my function. Okay, so in this function, I define all of images. I have total 179 images. Each image, every image I clip with my study area, every image. So now in this case, when you use this type of function, you don't need to use the clip function again in here, don't need, because I already done this step. I already clip every single image using this function in my collection, total 179. Every single image I simply clip with my study area. So that's why if you just ignore this part and run the code and add the layer, then check what happened. Just I add the layer and run the code. Okay, we can get this type of result. You can see it just show only for my study area, because in this case all of images I have total 179 images. So each image I clip with my study area, as well as for every single image I just remove null value. So this clip part I already done in here for every single image. So that's why when I create the median, then not need to put clip again. Okay, because this step I already done in my function. Okay, so now we try to add the visualization. Okay, so let me try to add their color code. They already have some color code. Just I copy and then paste. And now from here just I call and paste after the object name. And in this case I want to check what is the best range for my study area for soil moisture level. I keep the 98%. So now it automatically showing me the range. So this range I further simply put in my min and max range value. So it show this type of range. Just I copy this value and paste here, and also copy this value and paste here and run the code. Okay, so we put the layer name. Suppose I put the layer name, it's a soil moisture. Run the code. So now again, so we find out this type of cell or grid. Okay, because this resolution is not much good. It show the 9,000 meter resolution. So we find out this type of cell. Okay, for this. So if you want, suppose I want to display it for the big study area. Suppose I just simply increase. So then we find out the more smooth map. Otherwise, it show this type of grid or cell, because this one cell is total your 9,000 meter. Okay, very high pixel size. So that's the reason we find out this type of result. Suppose I want to check for this type of study area. So now run the code. So now it look more better, but not much better, because it's very high pixel size. So when you work with a small study area for your suppose for cropland or agricultural land, then we try to use Landsat or Sentinel 2 or Sentinel 1 to make the soil moisture to more better idea about that your soil moisture. So now if you check, we find out this type of data. So in this data, if you check the color, so for this type of red color indicating about the high soil moisture index, we find out this type of place. And this type of blue color, it's a low soil moisture index. Okay, so high soil moisture index, we find out this type of red color. Then blue is the low soil moisture index. And if you want, suppose I want to create a time series chart for a specific soil moisture place. Suppose I want to check for this, okay, and for a specific cropland or other things. So for that, simply click and then open. Suppose I want to check it, just zoom and find out agricultural land. Suppose I just choose this pixel. So I just take the new layer and put. Suppose this is my cropland area. Okay, so for the cropland, I take a new geometry of point. So for this point, I want to monitor suppose soil moisture for my growing season. Can I do? So for that, just make a time series chart. For that, take a variable, suppose chart, and apply suppose UI dot chart dot image dot series, okay, and put all of argument. So if you simply search here this function, then we can get all of idea ui dot chart dot image dot series. Okay, so now we try to check all of argument and put one by one. So first of all, image. So in this image collection, okay, so we already make the image collection. You can see this is my image collection, and in this image collection I already remove all of, okay, null pixel value. So I put the image collection, this is my s map, then I put the comma sign. Then after the image collection you need to put here, suppose region basically I just define the geometry. I put the point geometry, so this point I simply define in here geometry. After that, region, then reducer. So I have to compute, suppose just put here ee dot reducer dot first. I just take every image first value, okay, every image first value I just took soil moisture first value for every image, okay. After the I put here, suppose we find out the scale is the resolution. So I put the resolution in our satellite data resolution, it's a 9,000 meter. And further your system, I put here system time start, okay. So now this is my chart. I want to print the chart, just print the chart and run the code. Then we can get the soil moisture times reach chart for this specific land or crop land. So now if you check, we find out this type of chart, okay. So this chart, if you check for this time, so I put this is my growing season. But when you work with one study area, then you try to put the specific growing season, okay. So I put the randomly this time period. Or we can also put, suppose I take the data for 1 year, then check, suppose 2024 to 2025 January or 1st January, okay. So then we take the data year of 2024. Now let's check. So now I can easily identify more better phenological structure. Okay, so now you find out this type of soil moisture data for 1 year for this land, okay. So now if you check this data, so you find out this is the top soil moisture. So soil moisture basically in the remote sensing, it refers to the amount of water. It's a amount of water present in the soil within the root zone or near the land surface, okay. So we find out this type of value is very high, okay, in the high soil moisture 0.3. And you can see we find out then it also low, okay. You can see again, you can see very low, okay. Then you can see also high, okay, very low and very high we find out. And it's a key variable in agriculture, hydrology, climate studies and environmental monitoring, because it influences the plant growth, okay, and also water availability, runoff and road condition, everything will be controlled by soil moisture, okay. So soil moisture is basically it's one kind of data which give you the information amount of water present in the soil within the root zone or near the land surface, okay. And we can easily measure this type of things from satellite, it's a satellite data, and we can easily identify soil moisture, okay. We find out this type of soil moisture. And volume of soil moisture, it is a meter cube, okay. Water per volume per soil, its unit is the meter cube by meter cube. And soil, we can easily monitor, we can easily wetness or dryness we can also monitor using the soil moisture. If you check, we find out this type of red color, it's indicating about the high soil moisture value. So it means that this type of red color area, we find out that high soil moisture content, or this type of place water present is very high, the amount of water present is very high for this type of red color pixel, okay. We find out for this study area for this time. So this is one kind of data we also use to identify for soil moisture information for a specific land. So you can simply click and then suppose I put the red zone. So it show very high soil moisture content. So now run the code again. Or if you want, you can also compare. Suppose I just take some point. So this is my one. I want to compare, and then I take the another geometry, and I suppose this is my red zone. I take the another geometry. Suppose this is for this type of green zone. So now I just compare the three study areas. Suppose I have total three field. So it's one field, this is the another field, and this is the another field. So now I want to compare the three field soil moisture information for this three field. We can easily make the chart and do it. So for that we create the another function. So this function called UI chart image by region. Okay, series by region. So this such we need to use in here. So for that, just take a variable, suppose chart2, and I call UI chart image series by region. So this is my function to compare. I want to compare these three land, individual land, and okay. So these three, okay, sorry, we make a mistake in here. So these three things we are just need to take a one geometry. Okay, let me just, okay. So I take the new layer. Okay, suppose geometry R4, and this for suppose this is my one, this is the another field area, and this is the suppose another field area, or this is the another field. I take the total 4 field. Okay, so I just put the same geometry, 4 point I take for the same geometry, and further click on here and put it, it's a feature collection, and okay. So now I want to use this geometry 4 because it including total 4 individual crop land. So now I want to monitor this 4 individual crop land soil moisture information. So for that, just I use this function. Okay, in this function I need to define. So first of all, image collection. Sorry, what is that?
Sure, geometry 4, I don't understand how have you gotten it.
Okay, so this thing is not need, just I remove, then you can get the idea. Suppose in this time I take the individual. Okay, but when you compare, suppose you want to compare the data, you want to compare, suppose you have different field, and for the different field when you want to identify soil moisture value. Okay, then we simply use the same geometry. Suppose in this time, this geometry I stored different field in the same geometry. Okay, this one it's included 4 points. You can see this 4 point, or this 4 point I simply store it in the geometry 4. So now I want to identify this 4 individual field. I want to identify soil moisture data. Okay, for that I simply stored all of those in the same. You can see it stored total 4 geometry or 4 points in here. Okay, so I simply call the smap. This is my data set. Okay, just call this function UI dot chart dot image dot series by region. Okay, what is the spelling? Let's check. It's a by region. By region. Okay, so just use it. So first argument, image collection same smap, and then paste. Okay, then second argument you can check, it's a region. So regions, so my region is the total 4 study area, and it stored the geometry 4. This variable stored the total 4 points. Just I use at the 4 points. And now after that, define this geometry. Third argument is the reducer. So I put here ee dot reducer dot first. I just take the first values for each images, and then band. So band, it's your band name. So in this case my band name is soil moisture am. So this is my band name. Just I define. After that you need to define scale is the resolution. So I put the scale is that 9,000 meter. Then we need to define X property. X property we can put here, suppose system time start. Yeah, system time start. And you can also define the series property. I put the default. Suppose series property, basically it stored the crop name. Suppose this is the rice, this is sugar cane, this is so label of the total 4 points. So now just print the chart and then check what happened. Just print the chart 2 and run the code. Run the code. Okay, so you can see we can get this type of things. Total 4 crop plant. We find out this type of chart. This is my specific one crop plant. This is the another crop plant. This is the another crop plant. This is the another crop plant. Okay, so in this time I don't mention any kinds of name, but if you want, suppose you already know, suppose 0 is the rice, you already know. 1, this point is for suppose sugar cane, this is for the jute, this is the suppose another crop. So now we can easily compare. Suppose this cropland how much soil moisture we find out in the January 25, and this cropland how much find out the soil moisture in January 28. Okay, suppose you can see we find out that June 3 it's very high. So this cropland, suppose this is the rice. Suppose for the rice we find out that high soil moisture value for this time, and you can see find out the low, this type of low 3. So we can easily compare for the different crops soil moisture data. We can easily compare by using this way. Suppose you have a point, so this type of point in indicating different types of cropland. Okay, so now we can simply use this type of technique not only for this, any kinds of data set. Just apply the same process and identify different place what is the time series chart we find out, and then further we compare the soil moisture. So it's one kind of technique to identify for the soil moisture.
Is it possible to rename those 0, 1?
Yes. It's called the series property. Series property. You can see we have another series property. So in the series property, you can simply define. You can check the by region. We find out the last one in the series property. So in the series property, we can simply define. Then it will be work. Suppose series property, you can see it's the string. So property of feature, okay, or default system index. We can system index, basically in this time we are not put any kinds of label. Suppose if you check, we can also put here the series property, okay, property of feature in region to use the series label. Okay, default it's for the system index. Basically it will be start from the 0, then 1, then 2 and 3. But if you want, you can also put the series property. Suppose I just add some series property. Default I simply show you that. Suppose just I add the series property as a dictionary. So I put first, suppose it's a rice, I put the random. Okay, suppose rice.
Yes.
Suppose this is the sugar cane. Suppose jute. Then suppose barley. So now let's check. Okay, show problem, element property, valid, expected, actual type. Okay, we need to set the property.
Yes, we need to set when we are defining.
Yeah.
Yes, I understand.
So suppose when you define,
yes,
then we need to put the property name.
Yes, in the marker.
Yes, so you can see in this time you can see it show the ID is the 0. Okay, also you can see ID is the 1. So that's why I show the 0, 1, then 2, okay, and 3. But when you put the marker, just simply put the ID, then I hope it will work, no problem. So let's try. I hope you can easily get the idea how we can easily do it for that add the series property. But this is the process we can easily do using to make this type of comparison for the different types of cropland. Okay, not only for the soil moisture, any data, NDVI or anything. Suppose you want to, this is the sugar cane, this is the suppose rice, this is the suppose others. Then we can easily compare the more cropland in our one chart. Then we can easily identify which water need the more soil moisture, which cropland is more better growth. So this type of information you can easily generate from here. Okay. So now we talk about that another data. So this data set, okay, so I'll show you the example. Suppose I want to identify soil, bare soil. Okay, so suppose I want to identify bare soil. And what is the bare soil? Bare soil, it's indicating about the low NDVI value, for the bare soil, and we find out the SWIR. Basically, this is the one kind of band reflectance. We find out that moderate SWIR, this band reflectance, okay, reflectance for bare soil. So let's go try to identify using this condition. So for this study area, we want to identify for the bare soil. Bare soil basically low NDVI value and moderate SWIR reflectance value. So for that, we create a, suppose I create a function. Okay, just I create a function. I put the function variable name, suppose bare max, or identify for bare land or bare max. I put the bare max. So then create a function, keyword, element name, suppose img, and now put my argument. So what is my argument? So my argument is that I want to compute NDVI and also choose the low NDVI and also moderate SWIR reflectance, okay, which is indicating about the bare soil. So for this region, I take a variable, suppose NDVI, and I compute the NDVI using this element. I put here suppose normalized difference. Let me increase my zoom. Yeah, normalized difference between two band. First band is for near, second one is for red. Okay, and now I rename it as a NDVI. Okay, so I calculate the NDVI. And now what is the bare land? I take a variable, suppose bare soil or bare. This NDVI, I take the low NDVI. So I put here suppose less than. I choose 0.25. Okay, so I choose the low NDVI value 0.25. And
0.1.
I can also put the no problem, 2.1, no problem. Okay, so low NDVI value indicating this type of range we can put, there is no problem. So I put the low NDVI value, and then I put here suppose and another condition. I choose this, I select this band, select the band of SWIR, and I take that moderate reflectance. So moderate reflectance basically greater than 0.1. It's called the moderate reflectance for this type of band. So I put here suppose greater than 0.1. So I create this type of condition. You also change that this type of value, there is no problem. So now I find out I can compute the NDVI and also use this type of things. And now what I return. So I want to return this image will be updated. So put the update marks using this condition. Okay, so now I create this function. Now this function I want to connect with my image collection. Okay, so let's now we try to identify for image collection. So for the image collection, we just need to import a image collection. Okay, suppose just I just write the code in here. So I create a variable. I put the variable name suppose s2, and call the Sentinel-2 surface reflectance. I use this suppose Sentinel-2 because it's more high resolution. I call suppose Sentinel, or simply find out from here Sentinel. Sentinel-2 multispectral I choose, and identify surface reflectance. Okay, and this image, if you check, okay, it says one kind of scale. Okay, so this image color I simply copy and paste here, and also define filter bounds for intersecting with my study area, which is AOI. Then put the filter date. So I take the data, suppose I take this type of data, 2024. I take suppose 2025. So now it take the data 1 year, 2024 to 2000 January December. I take the data 1 year data. Just I define the year. It also work. There is no problem. And further, this is my image collection. Okay, so in this image collection you can see I don't filter the cloud level. Okay, so when you not filtering the cloud level, then you need to apply the cloud max function. Okay, so in this case you can also apply suppose filter date and apply suppose cloud pixel percentage less than 1. Just apply the filter metadata. Okay, suppose filter metadata, and further you can also filtering the cloud level. Okay, but when you use it the cloud level, then we don't find out the crop information, because suppose sometime less than 1% is not available. Monitor the cropland or identify for agricultural production or soil moisture anything, then don't use the filter metadata. Okay, but when I don't use the filter data, then we find out some cloud. So for that we create a cloud max function, okay, to remove all of cloud and get the very neat and clean satellite imagery. So for that, just take a variable. Suppose I put the variable name is that s2 cloud max. Okay, I put this type of variable equal. I put here suppose function and element name suppose image, and put the curly bracket. In this curly bracket I define my argument. So what is my argument? Just cloud filtering. Okay, so it's very easy. Just take a variable. Okay, we already discussed about this type of cloud max function in our 7 days online training program. You can get the idea from here. So I put here suppose image and select the band name. This band mainly QA60. So put here QA60. Okay, and then I take the 2-bit. Suppose I take a variable. Suppose I put the variable name is the cloud and call the QA it connecting. So put here the bitwise AND function for connecting with the band. So bitwise AND I put the 1 less than 10, so it's one kind of bit number, and I set not equal 0, and also put here the OR QA bitwise AND I put 1 less than 11, so this is the another bit number, and I set not equal 0. Okay, after that we simply return. Okay, suppose just I put here I want to return this image will be update max. So put here the update max function, update max cloud dot not. Okay, so now all of cloud will be removed. Just put the not function from here, and now divide, or you can also put the multiply with this value. This value basically our scale value 0.001. So this is the scale value. Just copy and use it. Okay, so now in this case you can see here in my function I also create another function near and red. So I create this type of band name, but what is the actual band name in my satellite image? If you check, it's the B1, B2, B3. Okay, so now this type of band name I need to rename. Suppose B2 I rename blue, B3 I rename green, B4 I rename red, B5 I rename suppose near red is. So I simply rename this type of band name. So how I can rename it? So let's go and try to show you that. So for that, just I use the code in here. Just put here dot select. Oh no, after return and multiply this function. Put here the dot select. I just make a list. Suppose I select the B2 band, then B3, then suppose B4. Okay, then put here B8 and put suppose B11 and B12. Okay, so now I rename it. So for the rename, it's very easy. Just put the comma sign and apply the another square bracket and put B2. I put it's a blue band. Okay, then put here B3. I put it's a green band. Then B4 is a red band. Then I put here B8. It's a near infrared band. And B11 is the short wave infrared 1 band, and B12 short wave infrared 2 band. Okay, just I define. So now it just select this band and also rename this type of name. Okay, so after that I simply use a copy properties. So copy properties from this image and also apply image dot property names. Okay. So this is the function. This function basically help you to remove the cloud as well as also help you to rescaling your scale factor as well as also rename this type of band. So this function simply connect with your image collection. So this is my image collection. So I simply connect using the map function. Just call the function variable name which is s2 cloud max. Just copy and paste here. Okay, so now it's connecting all of images this type of. If you check suppose just print and check suppose s2 from the code, so it image collection is computed. So now you can check all of image. We find out the new name blue, green, red, this type of name we find out. You can check just it working. Okay, so if you check, just click on here. So if you check the features, total 969 images we find out for this 1 year. Okay, and if you check the each image have this type of band blue, green, red. Okay, so just I rename it already. I rename it this type of name. So that's why it look like this type of name. And all of image is already remove the cloud and haze because I already apply the cloud marks function in my code. Okay, so now you find out this type of things, and I already defined the bare land. Okay, using this condition. So now this function I need to connect with my this collection. Okay, s2 collection. So for that you can easily connect using this function. So just take a variable. Suppose I put a variable name is take a variable. I put the variable name suppose bare soil composite equal. I call the this s2 because it is stored all of images. Just take copy and also define in here. I call the map function and call this function variable name bare max. Just copy and paste. Okay, and further I create the median composite and clip with my study area, suppose AOY. So now try to check the result. Suppose take a variable map dot add layer and we create the bare soil composite. Just copy and paste. And in this composite, yeah, please.
There is a difference in functionality between those that update mask function and self mask.
Yes. So update marks and self marks is the update marks basically in this time. Suppose I have I create this function, and in this function I set a condition. Okay, so this condition I want to update. Okay, So then we try to apply the update max function. Suppose you create a condition. Suppose in this time this is my condition. So this condition I want to update. So then put the update max function. And when you need the self max function we apply when you want to just apply the remove the suppose binary class. Okay, suppose I just have a two class 0 and 1, but I want to remove the 0, just keep only for the one class, then apply the self max. Okay, but suppose when we apply the condition, suppose this is my condition, this condition I want to apply and update my image, so just put the image and update max, then it will be work easily. Okay, for the update any condition. Okay, so now I just simply add the layer of composite. Okay, and just run the code. Let me check what's the problem. Okay, okay, so SWIR, okay, SWIR 1. It will be SWIR 1 because we put the name is the 1. Okay. So now if you just add the layer, suppose I put the layer SWIR, then put here the near, and also put here red. Stressing level was 98%. And apply. So now if you check, we find out this type of composite. Okay, so now you find out this type of place have the your basically it's a crop plan we find out. Okay, so this type of place, and this type of place we find out it's a bare land. Okay, we can easily identify this type of place. We find out that cropland or agriculture or vegetation. Okay, but others this type of things it show about that your it's a bare land we find out, or without cropland. Okay, we find out this type of things for this place. Now let me just import this visualization. Just copy. And it's called the soil brightness or bare soil composite. Soil composite. Okay. So now we talk about that soil salinity, how we can easily compute the soil salinity. So for the soil salinity, we need to apply the different types of index. If you simply search here, suppose soil salinity index, simply search. So there's a lot of formula you find out for the soil salinity index if you check. And you can see this also you can see that this salinity index, this it's one kind of formula, and this is the reference about that, or brightness index. So we also discuss about the brightness index about that suppose some time. And normalized difference salinity index NDSI. Okay, vegetation soil salinity index, you can see VSSI. So different types of soil moisture we are used for the different purpose. Suppose you can also read this paper, then you'll get a lot of idea about that, how we can easily apply the different types of formula. Suppose salinity index, brightness index, normalized difference, salinity index, vegetation soil salinity index, or normalized difference vegetation index, or soil adjust. You already know about this type of things. And you can see for that they also use the EC data to compare and make the classification. You can see the non-saline, salinity saline, moderately saline. Okay, and make this type of classification. Also check the result. You can see salinity index result and also ground truth data result. They also combine and make the regression analysis. Basically identify linear regression R value to compare the result. Okay, so you can see then they are make this type of, so this type of place non-salinity, then this type of place moderate salinity, then slightly salinity, this type of color. Okay, and this is the R square value. So one thing is neat when you work with salinity mapping for your study area, and we need the ground truth EC data. Okay, ground truth EC data we need to measure, okay, for the specific coordinate. So further simply just compare these two data, ground data and also satellite data, and create this type of map. Okay, for the salinity map we can also create, but we can also help of index we can identify which place is more high concentration of the salinity. This information you also get this type of index we are use, suppose salinity index or brightness index, normal difference salinity index. So this type of index we are using and identify. Okay, so let's go try to apply a formula and identify for soil salinity modeling and mapping using remote sensing and GIS technique. This basically they applied the sugarcane area irrigation farm. So you'll read the paper, then you'll get a lot of idea.
Yeah, that paper will help me because I'm writing an article about sugarcane prediction, yield
Yes.
prediction.
Yes. So you can see they also compute the regression coefficient value. Okay, but for that we need the measured EC data and create this type of mapping. So let's go try to apply soil salinity index. So one formula of the soil salinity index, basically NDSI equal, we can write suppose the band SWIR1 minus NIR, then divided by SWIR1 plus NIR, or you can put any formula for the different types of formula is available. So I want to compute it and identify for soil salinity. So for that it's very easy, just take a variable. I put the variable suppose NDSI suppose salt, and you can see here I already make the bare soil composite. Okay, because in the soil salinity I want to monitor for the bare land, okay, where have the low vegetation and it's not affected my result. Otherwise if I just apply it for the vegetation, you can see we have also another indices for the vegetation soil index. Okay, so this index help you to identify for the soil salinity in the vegetation area. Okay, but in this time I am to apply the normalized difference salinity index. So further we first of all we simply separate the bare composite, bare soil composite is simply separate bare land. Okay, we find out this type of place is the bare, and this type of place we find out the vegetation or crop and others. So this is the way we simply identify bare soil. So that's why I simply put the bare max function and also connect with my satellite image and create the bare soil composite. So now when I compute the salinity, soil salinity for the saline, just call the bare soil composite and apply this formula, NDSI formula. So just put here normalized difference between SWIR1 and near infrared, so NIR. Just I put it and I rename it as a suppose salinity index, salinity index. So now we try to add just map dot add layer and call the ndsi sort and run the code. Well, let me take the small study area forward and it very quickly get the result. Just I take only for this. Suppose this is my crow plan. I simply choose it. Okay. Yeah, I put it this type of I say put the randomly. Okay, to get the result. So now run the code very quickly can get the otherwise take some lot of time. Yeah. Okay, now we try to add the color for the salinity index. Just stressing I keep the 98%. And I put suppose low salinity
That's the problem. Sometimes,
yeah.
up to me. I don't know why.
So click on let me check again. So I think some problem for networking issue then this code editor is not work properly. Yeah. So I want to add the color.
It normally happens. That's a problem.
I just run the code again. Just a minute, let me add the color randomly. Just take a variable, suppose pi is trying to add suppose mean and max value and make the color plated. Suppose it show the green color for the low salinity greater than yellow color and high salinity show the red color. I put this type of color and this mean max value I simply take from here. Just copy this value and paste here mean, copy and paste at the max. So now further just copy the visualization parameter and add in your object and put the layer name suppose salinity. So now run the code. So now you find out you can see this type of things. Okay, so this type of red color indicating about the high salinity index. Okay, and green is the low salinity index, we find out in here. And this type of yellow is the
So
medium.
saline
Yeah.
soil salt, soil salt,
Yes.
high concentration of salts.
Which one?
High salinity. Salinity means the soil has high concentration of salts.
Yes, 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 yes. High concentration of the salt or salinity. This type of plug we find out. Okay, you can also check the value. Suppose just click on here and it's a index, but when you apply the regression with your EC data, just use this type of paper, then we can easily identify, we can easily make the classification. Okay, there you can see we can easily calculate the non-salinity, salinity, or the salinity, but further we need the EC data. But we can easily identify using the remote sensing index. You can see different types of index we are used to identify for soil salinity concentration. Okay. Suppose high positive value indicating the high concentration, low salinity value indicating about the low concentration. So this type of things we can easily find out from here. Again, this paper basically there is a landscape image for the different time. Then you can see salinity and vegetation index generation using this type of things. Okay, and further they also collect the data from primary data, EC data, and pre-process the data correlation, then model generation, then soil salinity change analysis, and predicted the soil salinity risk map. They are also create. Okay, using the machine learning, I thought. Yeah, and there you can see it's one kind of practice for the making the research paper. Also, you also try to identify for any study area, then it's also best practice to make the publishing the scientific paper for the salinity modeling, soil salinity modeling, help of EC data.
Send me paper.
Yeah.
You will send me also that paper.
Okay, no problem. It's fine. No problem. So after the salinity, we can also identify for soil brightness. Okay. Suppose soil brightness, we can also apply the different types of things. So let's we try to apply the compute the soil brightness. A soil brightness basically it refers to the how reflective the soil surface appears in the satellite or aerial imagery. Okay, or brightness is also related to the albedo reflectance of the soil surface, and bright soil reflect the more light and appear the lighter in satellite images, while darker soil absorb the more light and appear the darker. Okay, suppose brightness soil is reflect the more light and appear the light, and while the darker soil the soil absorb the more light and appear the darker. Okay, and we can find out the factor affecting. Suppose lot of factor is affecting by soil brightness, such as soil, I'll slide the factor name, you can also study later. Suppose one factor for soil moisture. Okay, soil moisture is also influenced by brightness. Okay, wet, I put the example. Suppose wet soils absorb more radiation, more radiation, more radiation. Wet soil, okay, more radiation, or lower brightness. We find out in here. We find out the lower brightness for that. So second factor, suppose we can say that organic matter. So organic matter. So organic matter, what happened for that? Higher organic matter. Suppose higher organic matter, it look like your darker soil. Okay, darker soil. So if we find out the darker soil, it means that this soil have a higher organic matter. Okay, and we find out that in the darker soil we find out that lower brightness. So you can see using the brightness we find out the lot of factor for the soil. Okay, so I'll write this type of thing also. So organic matter, basically we find out the higher organic matter, we find out the darker soil, and darker soil lower brightness value we find out, lower brightness value we find out. Okay, second argument, suppose it can be your soil texture. Soil texture, for the soil texture what happened, for the soil texture, um sandy soil, suppose sandy is one kind of soil, sandy soil is one kind of type of soil. Sandy soils are, we find out, are generally brightness. Okay, generally brightness sandy soil. Okay, generally brightness, generally brightness than clay soil. Clay soil. So we can also identify this type of soil texture based on the soil brightness. Okay, sand, suppose another factor, we can say that salinity. For the salinity what happened, soil salinity what happened, so saline soil often appear brighter. Okay, so saline soil or salinity soil, we find out it's appear brighter, due to the salt crust. Okay, due to the salt crust we find out it's better, due to the salt crust. So this is another factor which is influenced by soil brightness. Finally, we also saw that another important thing, it's called the surface surface roughness. Surface roughness. Surface roughness. So how? So smooth surface reflect more light. Okay, smooth surface. Smooth surface. Smooth surface. It reflect more light. More light. Uniformly. So you can see based on the soil brightness we can easy this type of matter, soil moisture, organic matter, soil texture, salinity or surface roughness is different on the soil brightness. So from the soil brightness we can easily identify different types of things. Suppose you can see soil moisture, wet soil absorb the more radiation, so that's why you find out the lower brightness. Okay, so for the soil moisture, wet soil, it show the lower brightness value. Suppose I find out the lower brightness value, it means that it wet soil, okay, and wet soil have a high soil moisture value. Okay, because soil moisture is the content of water in the soil. Organic matter, you can see for the organic matter what happened, higher organic matter, it look the darker soil. Suppose I find out this place have a darker soil, mainly lower brightness. Okay, and this darker soil have the higher organic matter. Okay, same, suppose soil texture, sandy soil are generally brightness than clay soil, we can easily identify it show the more brightness, so it's sandy soil, and clay soil is the darker. Then salinity soil appear the brighter due to the salt crust. Okay, and finally surface roughness, we find out the smooth surface reflect more light uniformly. So now we compute the soil brightness, how we can compare, discuss about that. So for that, I just call to take a variable. Suppose I put the variable name is that it's called the normalized difference brightness, or let me check for the formula, NBR2, NBR2 index, simply search, suppose, okay, index. Normalized difference burn ratio. We identify NBR2. So burn ratio we try to identify. Okay, which is the more burn. More burn mainly more reflectance value. So we try to apply this formula. If you check the formula for that. Okay, I think some networking issue. It takes some time. Okay, you can see this is the formula about the NBR2. So this NBR2 basically SWIR1 minus SWIR2 divided by SWIR1 plus SWIR2. So this is the formula. So let's say we try to apply this formula. NBR2. So just I call the bare soil composite. I already make the composite. In this composite, I simply computed this formula. So just paste here and apply normalized difference. Normalized difference SWIR2 and SWIR1. Okay. And I rename it dot rename SW or rename suppose NBR2. Okay. So now let's try to apply this at the layer map dot add layer and call this, just copy and run the code. Double I put this depth color for the lower soil. What then I put here? Let's apply. So you can easily find out now this type of place. Okay, if you check and just simply compare with the color. So we find out this type of place have the lower value of soil brightness. We find out this type of place. Okay, and this type of green color we find out that it's a higher. Okay, so now you can simply compare the different types of factor. You can see soil moisture, organic matter, soil texture, salinity, and surface roughness. We can just compare with the high and low value about that. Okay. Or if you want, you can also apply the composite also. Suppose for the soil brightness, simple albedo is also apply. Suppose just take a variable. I take a variable, suppose bright. In this variable, I just store it the call the bright. This paired soil composite I just call, and then I just select this type of bands. So this band basically suppose select for blue band, then green band, then I put here suppose red band, then SWIR1, then SWIR2. Okay, so I put all of those, and now this type of from this band, all of bands, I simply reduce. How I can reduce? I just apply the EE dot reducer dot mean. I compute the mean average value, average pixel value for each bands, and I rename it as a bright. Okay, or soil brightness or soil bright. So it's one kind of way. We also try to check it. Just map.that layer and call the bright and run the code. So you can set the color. Suppose I want to just stressing 98% give and add the, suppose I just put the darker soil. I put this type of darker, then put here, this is the this type of color, and also put this type of bright soil. I put this type of white color or this type of color, and okay. So now if you check, you find out this type of result. Okay, so this type of color indicating about the darker soil. Okay, and white is indicating about the brighter soil. Reflectors I find out from here. Okay, suppose like, let me check suppose stressing level. We can then check. Okay, you can see find out darker. So this type of darker, it's a bright soil. This type of white color. Okay, and if you compare the result with the NBR2, you can see we find out the almost similar result. Basically, this type of color indicating about the darker soil. This type of place, and if you compare with your this soil bright layer, we find out you can see almost similar. Okay, almost similar. We find out in here. And you can see this type of green color, it's indicating about that your brighter soil. So further you just compare with that, we find out the white color. You can see this type of white color we find out in here, this type of white color we find out in here. And from here you can easily identify, because soil brightness it's influence lot of factor we find out in here. You can see soil moisture, organic matter, soil texture, salinity, and surface roughness. We can relate it with this type of soil bright. So now further just import and then copy and then paste and put the, it's suppose I put it's a soil brightness. Okay. So I hope we can get the idea about that, how we can easily monitor this type of things. Okay, for soil brightness and the soil salinity or bare soil composite, how we can create. Okay, bare soil composite basically lower NDVI value and moderate reflectance value of the SWIR. We just apply this technique and identify what the bare soil composite and then create this type of things. Okay. So now visualize the interpret the layers, the agronomic decision. We can take different types of decision. Where is the higher nutrient? Where is the lower nutrient? Okay, as well as where is the high soil moisture? Where is the low soil moisture? Based on the soil brightness or salinity or NBR2, we can easily get this type of things. So now it just show the example about the code and data set. Okay, we are just use the soil moisture. Okay, and max field value, you can see we already use the -999 to remove all of those. And we use this type of Sentinel 2 processing. Okay, cloud marks we are use this band QA60, and surface reflectance we are multiply 0.001. Okay, and we rename this type of band. Okay, just I put this type of things also. And further for the bare soil composite, we are just put this type of logic. Suppose NDVI compute, and then bare marks we are just use this type of technique to identify for the bare marks and apply marks per images. Okay, create the median composite to reduce the noise, and further we display the mineral or soil contrast composition. Okay, SWI environment, right? Just show the visualization. And then soil health, you can see for the soil health we are just compute the soil salinity. Okay, salinity risk indicator, we just use this formula. And also clay or moisture thermal, we are just use NBR2. Okay, and soil brightness we are simply calculate the average value all of pixel. Okay, further for the validation we are just use the ground truth data, basically EC data or texture data or soil organic carbon data. Okay, before the decision we are just check this type of ground truth data and make the decision. So this is the visualization, and okay, this is the code I also add in here. It's not neat. I also send you all of code link, so from the link you can easily get the code, no problem. So now okay, soil, okay, we already discussed about that NDCI validation. Yeah. Okay, so now you talk about that optional extensions in one witness RWI. Okay, so now we talk about this type of topic. Okay, water balance, how we can easily monitor for the water balance, monthly precipitation and evapotranspiration and water balance, suppose a specific duration of time. Okay, for the monthly precipitation or evapotranspiration or water balance for a specific time range. So first of all, simply select our study area. Okay, then put the time period, and we just temporal aggregation monthly sum created from the source image collection. Okay, so you can put any satellite image to take the precipitation data. Okay, in this time we just use this data. You can see the charge painted data. Okay, and precipitation per 5 day we find out from here. And we also use at the for ET data we take the Moody's data. Okay, and we compute the monthly total sum painted, and also 8 day evapotranspiration within the each month we computed. Okay, and then we just identify for the water balance concept. You can say this is the monthly water balance simplified. We just use this formula P minus ET. Okay, interpretation. So let's go I take the practical example, then I explain the theory. So let me open the code editor. So first of all, I simply choose a study or cropland area. Suppose yeah. Suppose this is my study area. So this is my study area. Okay. So just I put the name RY. So now I simply work with first data. So first of all, I simply define the time period. Suppose take a variable start year. Suppose I want to identify water balance between this time period from 2010 to take the end year. In year 2020. Okay. So now we create the take a variable, suppose start date, and define the date dot date dot from year month day, and define the date. Just call the start year, and I put suppose 1st January, first date. Take the another variable, suppose in date. So dot date from year month day YMD, and define the in date this in date we simply put at the suppose plus 1 and 1 and also 1 I put in here. So I define the start date and end date, and also make the year sequence. Just take a variable, suppose years, and I put dot list dot sequence. Put here start year. I just make the sequence of year and in year. Okay. So define the start year and in year, and also make the list of month. Suppose I take the variable months and make the list dot list sequence. Put the 1 to 12, basically January to December. We put the 12th month for this year. So this is our first step. We simply define our time period. So now simply import the import your image or image collection or data set. We are just use the one data charts. It's a precipitation data we find out daily and painted. I use the sum painted. So this data set we try to use to get the monthly precipitation data. Okay, this data set basically we show the result is the one custom time unit. We find out the data millimeter 5 days. Okay, interval is the 5 days for this data. So just copy this painted data and take a variable, put the variable name, suppose charts equal. So now simply filter dot filter date. Okay, in the filter date, simply define the start date and end date. So I already defined, you can see start date. And also define the end date. Okay. So just I simply put the start date and end date. So now what my argument? My argument is that I want to compute it monthly precipitation. Okay, suppose each month total precipitation I want to compute. Okay, so this is my data set. We find out, if you check how many images, we find out, just print the charts. Okay. Okay, so here let me check. What's the problem? Number dot year. Oh, sorry, it's a India. Okay, we find out the 792 images collection. So now we try to create the monthly total precipitation. Okay, so let's go to take a variable. I put the variable name, suppose monthly precipitation. Okay, so in the monthly precipitation, I have a total 792 image collection. Okay, so this 792 image collection, I need to create the monthly image collection. Okay, monthly total image collection I need to create. So for that, we just use a function, this function called ee dot image collection from images.
Capital F.
ee dot image, yeah, image collection dot, yeah, so this function, yeah. So ee dot image collection from images. So I have a image collection. So this image collection I convert into other image collection. So for that, we are just applying this ee dot image collection from images, this function. Okay, suppose I have a 792 image collection. So this image collection I convert into monthly image collection for each year. I have a total 10 years data, 2010 to 2020. So for each year, I need to calculate monthly total precipitation for my study area. So just I use this function ee.image collection from images, and then and put here, suppose just create a function. Suppose I create a function. Okay, I put the element name, suppose y for year. So in this function, we filter our image collection. Okay, and okay, so and I want to filter yearly and monthly at the same time. Okay, so for that we define return months. I already defined the months, you can see I already defined the months. Okay, months. So return this months, it connecting with our function map, and put the function keyword again. Okay, and then put the element name m, and put our argument in here. So in this case, I create a function. I create the two function. First function for year. Okay, so this year function, it's come from this years. So we need to connect it. Just I copy and connect with my function. So map, I just define again and also close. Okay, so now you can see I create the two function. So first function years. So I take the each year. Suppose each year basically 2010 to 2020. I take the each year and also take the each year 12 month. Okay, each year 12 month. So for that, I just create the ee.image collection from images, and then I take the years. Okay, this function I connect with monthly. Okay, monthly. Two time I just use the function. So now we try to filter. So for filtering, take a variable. Suppose I put the variable name is w. You can put in name w, and call our data set. This data set total 792 image data set. It is stored in this variable. Just I copy and paste here. So this data set I want to filter. So just put here the filter, and in this case I want to filter using the calendar range. So put here ee dot filter dot calendar range.
Capital C.
Yeah, second. Okay, calendar range. So you just apply the ee dot filter dot calendar range. So in the calendar range, first time we filter yearly. So put here y. It's our element name y, and unit is year. So first time we filter for yearly, and second time we also filter for monthly. Okay, so for that put the filter again. I want to filter earth engine dot filter dot calendar range. Now we filter monthly. So put here monthly and put the unit is the month. Okay, so now we put the filter monthly, yearly is year, is month. Okay, suppose 1 year 12 month. Okay, so now we calculate the total precipitation. Just put here the dot sum. So now this is my argument. I want to return. I calculate the total sum. So I again explain this code again. So if you check, first of all, I have total 792 image collection for this time period 2010 to 2020. Okay, so now this 2010 to 2020, I compute the monthly precipitation for each month, for each year. Suppose 2010 total 12 month, then 2011 total 12 months, 2000 up to 2020 all of year have a total 12 month. So for that I create this function ee.image collection, and first time I connect with years. Okay, so this is my function for years, and from this years what I return for each year 12 month, for each year 12 month I return. So this is my argument. So for that I simply return months, and its month including total 12 months 1 to 12, and I want to function month. So now after creating the two function, so I filtered this image collection. First time I filter yearly. Okay, second time I filter monthly. It means that suppose year 2010 January, year 2010 February, year 2010 is month. Okay, each month we just generate the total precipitation. Okay, so now yeah, please.
Is it possible to filter even those rainfall per day?
Which one? Don't understand.
We have filtered the total precipitation per month and per year, is it?
Yes. Suppose month is year all of month.
Yes. Now I'm asking, is it possible to filter again from those months per some of the precipitation per day, because the CHAPS data provides precipitation data per day? Is it possible also to filter per day from those months?
So if you want, you can also put the seasonal. There is no problem. Then simply put the season time. Suppose you can say I take the January to December. So you can put here suppose March to May, or any specific time. You can put any specific season. You can also change the time in here. Okay, then it will be work. No problem. Same code. But in this take the 1 year, January December. Okay. So now what I return. So let's go ahead to return. So after get sum, we just simply return. So put here return this W set with first time year and put the Y, then set with again set with month and put the M. Okay. And you can also apply suppose dot set system time start and define EE dot date from YMD. So just we define the format EE date dot from YMD. Okay. And now put suppose year, then month, and date suppose first. It show the this type of things YMD. So now this is the function we define in here. Okay. And now in this function we just simply create the monthly composite. Now let's try to print and check what happened. Just print and monthly precipitation. We try to check the result from the code. So if face a problem, it show the what is the problem. Image collection precipitation. Unknown bands. Okay.
Oh, sir.
Yeah.
We didn't select precipitation.
Okay, let me check. For that we
From the data set.
suppose let me try to
You see?
select.
Yeah.
Okay, we try to apply the another function. It's called flatten. Now let's check. Yeah, so now it's what? So flatten function basically it convert the list. Suppose you can see it's convert the nested list into flat list. Okay, just we define the flatten. So now if you check the result, it total 132. Okay, and we find out the month. You can see every bands have a one band, and this band name is the precipitation, and we find out you can see the month one mainly January year 2010. So now we can check. We find out that is month. We find out that for year 2010 February. So then check. You can see this is the March. So all of we create all of yearly. You can check. Finally, last one is that we find out the 2020 December. So now it's convert the is year monthly data. So you can find out in here. Okay. So now this is my collection. We simply add this collection. Or if you want, you can also display the result. Just add the map layout. Okay, and also display the result. Or if you want, you can also make the time series chart. So we try to put the time series chart. Suppose then display the monthly, annual time series chart. So take a variable. Suppose chart monthly. So just put here UI dot chart dot image dot series by region. Okay, by region, and put all of argument. First argument is image collection. So we already make the monthly precipitation. Okay, just I put. Then second argument is study area, which is I put the name ROI. So put here ROI. Second argument, I compute suppose EE dot reducer dot mean average, and then put band name. Basically precipitation. It's a band name. Then scale is the 5,000 meter. Then we have to put here X property. X property basically system time start. System time start. Okay. And further, if you want, you can also put here. Suppose just use here set series name. I put suppose set series names. Set series names. Okay, I put the name suppose P for precipitation. I put series name. Okay, and then we also put the set chart type. I create suppose column chart. It will look better for the precipitation, monthly precipitation. Put the chat set chart type. And put the type is column chart. Column chart. Okay. So now print the chart and check what happened. Just print chart monthly and run the code. Oh my god. C O okay. C is the uppercase, I think. Yeah, C O.
No.
Yes, so now you find out, you can see for each month precipitation. Okay, so you can see this is the month January. Okay, so you can get the each month precipitation from 2010 to 2020. You can also add the chart title or lexible title. You can also try later, add later, same process. So now we just create this type of things for the precipitation. So after creating the precipitation, then we need to calculate the evapotranspiration, because we want to calculate the water balance. For monthly water balance we need to compute. Okay, so for the two things we need, first we need the precipitation data, monthly precipitation data we need. Okay, and then we need the ET data, ET mainly evapotranspiration data, evapotranspiration data. So this data we can get from modis, so we can simply call the modis to compute the evapotranspiration. So I simply search here modis evapotranspiration. I think this data, run it, evapotranspiration, this data. Okay, it's 8 day. It's net evapotranspiration available from 2000. Yeah. Mode is global terrestrial evapotranspiration. Yeah. It's the evapotranspiration. So we try to use it. Okay, so just copy, and band name is et. Okay, also have a scale 0.01. Okay, so just we try to use it because it's available from 2000 to 2014. Yeah, but we need the past time data. Okay, 2014 only.
You can use the climate data.
About transpiration, I think this data, let me check. 2002, what is the time period? And this band name is also et. Total evapotranspiration 0.1, same scale. I think this data set, let me check. Yeah, it's also okay, so we try to use it, and it also high 500 meter only. Just like copy and paste. Okay, and then give a variable name. I will put the name is that evapo. Then we can just simply put here the dot select and select the band name. Band name is et. So now further filter date or filter date and put here start date and end. We already defined the start date and end. So start date and also put that end date. Okay. So just we already define, you can see start date and end date. Just put the start and end date. So now these things we also apply. We are just use the same code. Okay. Suppose now not need to write again. So just I copy the same all of code because we just apply the same process again to create the monthly evapotranspiration value for each month, for each year. Just paste here. Okay. So now this is my image collection. So I put here, suppose this is the monthly evapo. You can put any name. Okay. And now this is my years, this is my month, and this is my data set evapo. Just I paste in here. And I computed the total evapotranspiration. Okay. Sum for each month. And this data set have a scale. Okay, this scale is simply used in here, just multiply. Scale is the 0.1. Just I use the scale also in here, and others just keep the same. Okay, so now we are just display the monthly evapor result. Just copy and paste, and also make the time series chart. Okay, and scale is only for 500, I think. 500. Scale is 500, and also put here the band name is et. Just put the band name is et. Et is the band name, evapotranspiration band name. I put the et. Yes. And also put here the series name I put here, so it's a et or et. Others keep the same, there is no problem. Just run the code. So now let's check what happened. So now yeah, it computed the total evapotranspiration for each month times the chart.
Done.
Yes, please.
It is done.
Yeah, it's done. You can find, you can see. So this is the precipitation for monthly each year, and this is the evapotranspiration monthly for each year, each month. We find out. So now I have ET data. I have also precipitation data. So now I can easily compute it, the water balance. Okay. So basically, what is the water balance? Okay, so now let's check the some theoretical part. I will show you that from my slide. Where is the slide? Yeah. So water balance basically WB equal precipitation minus evapotranspiration. So it's called the water balance. This is the water balance equation. And interpretation, water balance greater than 0. Suppose this value, if greater than 0, it means that runoff potential or recharge. And if the value less than 0, then we find out the deficit or irrigation need. Suppose some place I find out WB is negative, water balance is negative. It means that this type of land or this type of crop land, you need the irrigation. Okay. And suppose here I find out that water balance greater than 0 value, mainly positive value here I find, it means that there's a lot of water, resource or runoff potential, this type of place don't need any kinds of irrigation. But if I get the value water balance is negative, water balance value is less than 0, it means that you need the irrigation need or deficit of water. Okay. So in this time, ignore the soil moisture storage runoff. So in this time, you can see we simply ignore this type of things. Okay, just we can talk about only for that water balance based on the precipitation and evapotranspiration. But also water balance is also different some other factor. Suppose soil moisture, runoff, deep percolation, or capillary rise. Okay. So in this time we are just use the water balance screening the indicator field variation is recommended. Okay, so when you just take the scenario in your imagery, but when you take the decision you simply field validation recommendation you need. So let's go try to compute water balance and check the water balance value for each month. Then we can easily get the identify. This month I find out the negative value, it means that this month I need to irrigation. Suppose this month I find out the very high value of water balance, it means that you don't need the irrigation this month. Okay, so let's go try to compute the water balance. I hope you can get the idea. Okay, so now I want to compute the water balance for each month. Each month water balance I compute. So take a variable water balance. Take a variable, suppose WB equal so in this case we say apply the water balance. Okay, this we try to apply suppose dot image collection from images. Okay, and we computed two things, suppose yearly and monthly. So monthly water balance we compute. For the monthly, we create a function for first time for year. So function, this function for year, I put the year, and then what is my argument for each year, for each month. So I want to return month. It is connected with the function. I put the element name m, and what is my argument? My argument is, and these things, this monthly I connect with my years. So just put here the years dot map, close the bracket, and also close the bracket. Okay, so now we can see this is my years, this is my month. I already defined the month and years. Okay, so now we create years.map and return this month map function. Okay, so now what is my argument? So my first argument, I take a variable, I compute the p, mainly precipitation I compute. So this p I computed from the charts. So just I call the charts, and I filter. So just put here the filter, how I can filter, earth engine dot filter dot calendar range. Calendar range, first time we filter yearly. So year, unit is year. Okay. And second time we filter monthly. So put here the filter monthly. So filter earth engine dot filter dot calendar range monthly. So m unit is the month. Okay, so we filter it monthly for each year, this precipitation, and we computed sum total. So this is our one parameter for precipitation, for monthly precipitation I computed. So now another, take a variable, it's called the et, mainly evapotranspiration I call, and I call the data set for evapotranspiration. It's come from evapo. In the evapo I filter, so put here the filter, how I can filter, earth engine dot filter dot equal, what's equal what, sorry, filter how, calendar range for year, and also unit is year. Okay, then second time we filter for monthly dot filter calendar range and month. Okay, so we find out that evapotranspiration and precipitation, we compute the total. Okay, just put here the sum, and evaporate scale value, simply put the multiply the scale value, this is 0.1. okay, it's a scale value. So now if simply apply our equation, so what is our equation? Take a variable, suppose I put the variable name is wb equal, I call the precipitation p, this p, then subtract with et. This is my formula for water balance. Okay, so now I just rename it as a wb. So now what I return from this function, so just put here the return so I will return wb set with year, and also element is the year, and also set with month. So put here month set with m, and also set system time start, and define the date format, ee dot date dot from ymd, right? Year, month, day, and I define suppose year, month, and date, suppose first date. So I simply set this type of things. Okay, and finally we define the function in here flatten, otherwise it show a problem. So just put here the dot flatten. Okay. So now we create the water balance, okay, monthly water balance for each year, for each month. So this thing you also try to apply the chart and display the water balance, same process. Okay, so just like copy the previous code, this code I simply copy to display the water balance for each month, just paste, and now simply change. I just call the WB, this variable, and paste. Then ROI, it's my study area, I computed average, okay, and put the bare name. Bare name, I put the bare name, you can check, I put the bare name is the WB. Okay, and we define the scale 500, system will start. I put the series name, suppose WB. Just run the code. So now we find out the water balance. Okay. If the water balance value is the negative, if you check, we find out the lot of negative. So from this water balance, we take a decision. Okay, which month you need the irrigation and which month you don't need the irrigation. Okay, so if you check, we find out the negative value. First time we find out the negative, okay, less than 0. So then January we need the irrigation. Then check this month also, this month also. You can see we find out it's a positive or a positive value or greater than 0. So this month don't need the irrigation. This month we need the irrigation. Also you can see this month we need the irrigation because it's a negative value. So if the water balance is negative, it's indicating you need the irrigation. Okay, if the irrigation or deficit the water, and if the water balance is the less than greater than 0, it means that lot of resource of water or runoff potential for your for your land. Okay, so this thing we can easily identify using the water balance concept, for where you need the irrigation, where you don't need the irrigation, which month you need the irrigation, which month you don't need the irrigation. We can easily get this type of idea from the water balance concept. Okay, in this time we are just use the study area, big study area, but if you want you can also apply these things for the small cropland. Suppose I just simply take a new geometry. Suppose this is my cropland. So this is my cropland. Okay, so or you can also digitize your circle or put the buffer study area for the cropland, and further you can just use the geometry. Suppose I just put here the geometry. I need the result for my geometry. Geometry is my land. Just run the code. So now we can find out the result only for my this geometry or this land. We find out the result. Okay, we find out this type of result. I can see. So for the specific cropland or specific things, we can easily identify. Just simply draw your study area or take the point, okay, or create the mention here. Then you can easily get this result for the specific cropland, for the water balance need or when don't need the water irrigation. This type of information decision you can easily take from this water balance concept. You can see. Okay, so I hope you also get the idea about this concept. Okay, any question you can ask me. Okay, now suppose I want to visualize the map. Okay, suppose in this case we try to display the map. Okay, display the map, we can easily get the identify for that water need or which place need the water, which place don't need the water. So let's go try to display about this type of things, how we can easily do it. So for that we simply visualize our water balance map. Okay, water balance map we can easily visualize. So let's go. I try to show you this process. So for that, just simply map dot add layer, and I call the WB, and then apply. I compute suppose 2 bands. and then clip with my study area, which is name is, I put the name RY, so I put here that ROI. So now run the code and see what happened. So now you can check, find out this type of result. Okay, basically it show the different month. Okay, suppose this is the January. I want to show suppose only for the January. Suppose single. Suppose January 2010. Okay, and I custom stressing 98% and apply. And now if you check in the month of January, suppose I put, it's not work, just a minute. Or I take the more big study area, then it look more better, because in this time we're applying that chart satellite data, okay, which is not better. Just run the code, it work for the more better map. We find out for the big study area, okay, for the visualization. Okay, just click on here and click on the bands one. I took suppose January, February, March, April, May, June, July, August, September, October, November, December. Okay, then simply you can see January, February, March, all of those. We can easily get the all of month. So I want to display suppose January, stressing level 98%. Put the color. Suppose water deficit, I want to show this type of color, red color. It needs the water irrigation. Then less the greater than this type of yellow color. Then suppose this type of green color, and water put this type of color. So now apply. So now you find out this type of map. If you check, so now this type of red color indicating about that water deficit area. Okay, so this type of place, if you have the land or agricultural land, for the month of January you need the irrigation, this type of place. Okay, if you cultivate the any crop, then you need. But you can check this type of place have the lot of water resource. Okay, then don't need for the irrigation, this type of place. Okay, suppose this is the very high deficit, then suppose high, low, very low water balance. We find out this type of combination. So you also represent this type of, you can see this is the January, this is the only for the January. Then you try to check for the February, so you can see the second one, it's a February. Then suppose you check it for the January, February, March, this is the March. Then April. So any year we can simply check this way, all of monthly evapotranspiration, water balance map we can easily visualize and display. Where you need the irrigation, where you don't need the irrigation, you can easily get this type of idea. So we can see for this we find out this type of map. Okay, month of January, February, March, April. We find out this type of map. So in the April you need this type of land, don't need for the irrigation. But if you have this type of place, if you have need the land, so then you need the irrigation, this type of land. Okay, it's the moderate or high, so you can create this type of things. Okay, and visualize. And if you, in this case, when you work with suppose more small study area, so this type data is very good, pixel size is very high. But when you work with your more local region, then your data set must be very good. Then we find out the very good map. But it's also help you for the big study area. Suppose I want to monitor water deficit area for the whole country boundary of Bangladesh, or water balance for the whole country boundary of Bangladesh, then this data set will work very well. So I'll show you the results. Suppose just I simply import my study area. Suppose just I import this study area. So this is my table. So I need this result for this table and run the code. So now it's loaded for the whole country boundary of Bangladesh. So now you find out this type of result. If you check and now compare the result. So we're going to check for only for January 2000. stressing levels of NAQ 90%. Okay, or I will say suppose any specific other than suppose January, February to this date, or I put suppose this October. Okay, so just try to add the color. Apply. So now if you check compare the result in this month, okay, so you can see we find out this type of place, we find out the water deficit area, this type of red color. Okay, also you can see this type of place. Okay, you can see this type of place, it's very good water we find out for this type of place, also this type of place. But you can see this type of place, we find out the deficit of water. And if you have this type of area, if you have the cropland or also agricultural land, then you need to irrigation in the month of October. Yeah, so if you have the emergency irrigation this type of place, suppose this type of place don't need, also you can see this type of place also don't need. Okay? So we can get the decision from here for the large scale area. Okay, and also make the time series chart. From the time series chart you can easily get the idea for the water balance calculation value. If the value is the less than 0, it means that negative you need the water irrigation or water deficit. Okay,